Welcome to my lecture about the four basic operations. And by basic operations, I mean addition, subtraction, multiplication, and division. In a typical class setting, what I've done in the past is given you about 10 minutes to write, even just as a group, to write a definition of addition, subtraction, multiplication, and division. And the reason I've done that is because most people can't do it. Can you describe in real world settings what addition really truly is? What is subtraction? What is multiplication? What is division? Can you explain the process? Division is not taking numbers into other numbers. Multiplication is not taking numbers times other numbers. There's a concrete way of describing them. I'm not going to give you 10 minutes now, but we're going to talk through these a little bit. Before we do that, I just wanted to mention that a long time ago, the National Council of Teachers of Mathematics explained that there are reasons that we should learn or teach the meaning of the operations. As you probably know, it's not likely that we're going to encounter too many mathematics problems that we don't resort to using our calculators or our phones as calculators. So being able to do the process really well is not quite as important anymore as it is to understand. So these four key aspects of understanding the operations was proposed by the National Council of Teachers of Mathematics, probably before most of you were born, but I'm sure you can read them. I'm not going to read them right now, but there they are. As with counting and learning to count and learning number concepts that we talked about previously, with the operations, we need to go from concrete to abstract. We need to start with a real world setting or a real world problem. We use different types of models, and then we come up with the actual symbols that represent the answer. So when we go from concrete to abstract, in this case we're talking about concrete objects, we're talking about semi-concrete, which is pictures. Mental images are used as semi-abstract, and the actual language, like the addition sentence or the multiplication process, is the abstract, which results in symbols or answers. That's concrete to abstract in this case. So this Whoops, I kind of messed up the recording a little bit there. I'm back and you didn't know I messed up, I guess. So I want to talk a little bit about the actual definitions now of the four basic operations. Because we teach addition first, we'll just start with the definition of it first. And there's a reason we start teaching addition first. It's probably the simplest one to understand and the simplest one to show. The actual nerd definition is listed there. It's a binary operation. Each of the pieces of the operation have a name. In the addition situation, we call each piece an addend, and the answer is always unique to the two addends that we added. Thank goodness for that. If they weren't unique, it would mean that every now and then when we added 5 and 3, we got something different. And I don't think that's a good idea. So we do have a unique sum. It's called binary because of something that I want to show you. Do you know the answer to 5 plus 3? I know you can read it, but if I just set a problem to you, 4 plus 7, do you know the answer to that? I think you do. What about this problem? 4 plus 7 plus 5. Do you know the answer to that? Now compare how you got the answer to that to the answer to 5 plus 3. Do you know the answer to 4 plus 7 plus 5? I don't think you know it. You got it, you calculated it, but I bet you didn't really know it. you probably said, hey, that's 11 plus 5, or hey, that's 9 plus 7, or hey, that's 4 plus 12. You did a binary operation. You chose two numbers, and then you combined them, you added them, and then you added two more numbers to get the answer. And if you really get down to it, that's pretty darn cool, that we can take any numbers that we want, big or small, and break it down to just two numbers at a time, a binary operation. Subtraction has a similar definition to addition. As a matter of fact, we could just define it as the opposite or the inverse of addition. We oftentimes think of taking away a number or an amount, or comparing numbers or amounts. Each piece in the subtraction problem has a special name. I expect you to remember these because you are the teacher, and many math textbooks that you'll use in the classrooms use these terms. I can't imagine why you would teach them to children, but you need to know the terms. So we have a minuend, we have a subtrahend, and a difference. Here's the definition for multiplication. If you said taking a number times another, that's kind of what's happening. In math terms, it's usually called scaling. The best definition of multiplication is probably just repeated addition. In this multiplication problem, we have two numbers, but they don't mean the same thing. One number tells us how many groups we have. The other number tells us the size of the groups. So in the concrete world, you can think of this as 6 times 4. It means either 6 groups of 4 or it means 4 groups of 6. Now, children don't know that that's the same answer when you take 6 times 4 or 4 times 6. We do. They'll eventually learn that. But in a multiplication problem, each number has a specific name. The first number is the multiplier, the second the multiplicand, and the answer is called the product. Do you know 6 times 4? Do you know what that means? Does it mean 6 plus 6 plus 6 plus 6? Or does it mean 4 plus 4 plus 4 plus 4 plus 4 plus 4? Do you know the answer to that? Well, here's the answer. A multiplication problem has a very specific order. The first number tells you how many of the second number. So 6 times 4 actually officially means 6 groups of 4. Now division, maybe that's a hard one to define in your own words, but truly the best definition is probably just repeated subtraction. We do think of it as dividing, as breaking into groups. We think of it as splitting up a number by another number, but really it's just repeated subtraction. It's the best way to describe it. 32 divided by 8 equals 4. Each piece has a name. We have a dividend, we have a divisor, and we have the quotient. So in terms of repeated subtraction, think of it this way. How many times can we subtract 8 from 32 until we run out? We always love the problems that we come out with no remainder, or when you subtract you end up with 0, but in the real world that's not always the case. But the best definition, at least in my opinion, is division is repeated subtraction. We should give children many opportunities to solve word problems revolving around the basic operations. One thing that I would like to mention from this list that we should try not to do is we should try not to use keywords in word problems. Try not to teach them that this particular word means subtract and this particular word means add. try to focus on understanding the problem. When I was taught to do lots of different types of problems, I was taught to look for keywords, and I'm not sure that has helped me. So let's go back to addition. Much the same as when we talked about how many fish are in the fish bowl. Right now we have pictures of fish. What is wrong with this particular problem in the concrete or semi-concrete world? Why would some children say, hey, 3 plus 2, I don't understand, how is it 5? Look at the picture. How is that 5? That doesn't make sense. There's 10 fish there. At the concrete level, if you were using actual fish, it would look more like this. We would combine a group of 3 and a group of 2. That's really hard to do at the semi-concrete level. Right? So one of the ways we teach addition is at the concrete level and with groups of objects, combining them. The problem that we just did with actual fish or pictures of fish results in a number sentence. This would be the abstract. So you're looking at pictures right now, so that's semi-concrete. Ideally, we'd like to have actual fish, or say goldfish crackers on a plate, and use them to make the number sentence. But what we're trying to do is go from a problem of concrete objects to the abstract. This example really is at semi-concrete. So to model addition at the concrete level, there's really only 2 simple ways to do it. One is combining groups. The other is with a number line. The number line takes us beyond concrete and semi-concrete. It takes us into the semi-abstract world, where we have symbols and mental images of symbols. So if you're going to teach addition, or if you're in the you have the opportunity to do this, typically there's 2 ways to model addition. Subtraction occurs in the real world in more than just one way. Typically with addition, we have a group of objects, we get some more, that's addition. Subtraction, when we encounter it in real world situations, there's not just one way. The most common way to think about subtraction is with takeaway. In this example, a semi-concrete, of course, we have 7 fish. If we take 3 fish away, how many are left? That's real world subtraction, but it's called takeaway. So one way of showing subtraction concretely is with takeaway problems. There are other problems in the real world, though, that require subtraction, and they aren't takeaway. In this particular example, the question is really asking, if we have 5 and we need to get 9, how many more do we need? It is a true subtraction problem. The answer is 9 take away 5, but it's not takeaway. It's 9 minus 5 to come up with how many more we need. So imagine if you have $10 in your wallet, you need to have $12 to pay for something. How much more do you need? It's truly a subtraction problem. It's not takeaway. It's called missing addend. This example, I'll do my best to make it concrete, but it's still not concrete. But it's a subtraction problem. There's another way we encounter subtraction in the real world. There's no takeaway. There's no missing addend. It's comparison. One group has 12, one group has 8. What's the difference? In the real world, with concrete objects, we could compare them by crossing out, taking away, moving off to the side, putting X's on, whatever it might be. But there's not true takeaway. We're comparing the size of two groups. The problem that results is 12 minus 8, but it's not takeaway and it's not missing addend. Multiplication even has some more models for introducing the process at the concrete level. The first way, of course, is with groups of objects. Here we have 5 groups of 3. It's still semi-concrete, but it represents 5 times 3, or 15. That's probably the most common way. Another way, though, multiplication is often shown at a little more abstract level with a number line. Here we have 4 plus 4 plus 4. That's really modeling the repeated addition way. And by the way, don't forget that that's 3 times 4, 3 groups of 4, not 4 times 3. 4 times 3 would be 3, 3, 3, 3. Another model or way to show multiplication in the real world is with something that's called arrays. Arrays are simply rows and columns. It's important to show that you can find out the number of objects in an array by multiplying the length and the width. Of course, we start to call this area at some point in time, but early on in the multiplication process, we can demonstrate multiplication by using rows and columns. Using arrays, 4 times 6 and 6 times 4 can be seen as the same. 4 times 6 would mean 4 rows of 6. 6 times 4 would be 6 columns of 4. However, this is the way we can show very clearly that 4 times 6 and 6 times 4 are equal. Another way that is often used to show multiplication later on after the initial process of repeated addition is learned is by something called Cartesian product. It just means, really, it's a fancy math nerd term for combinations. So if I had all the different suits and all the different values of playing cards, how many cards are there? Well, it's 13 times 4 or 14 times 3. I'm sorry, 4 times 13. Think of it this way. If you go to Pizza Joe's, that's my favorite place in the whole world for pizza, and they have 2 different styles of crust and 4 different toppings, how many different pizzas could I make? There's no combining of groups. It's not a number line. It's not an array, it's combinations. 4 times 2, or 2 times 4. And by the way, for multiplication, this is one of the ways that it's really easy to demonstrate what happens when you multiply by 0. 4 times 0 is, 0. It's not easy to teach kids that. So think of it this way. If Pizza Joe has no crusts and 4 toppings, how many pizzas can I make? 4 times 0 or 0 times 4? I'm a sad guy now. There's no pizza. So we can demonstrate multiplication of 0 with Cartesian product. Alright, last but not least, we have division. Division is not terribly difficult to explain, but in the real world we encounter it in a couple different ways. One example of real world division is a problem called measurement problem. So I'll demonstrate this with animation. 28 divided by 4, in this example, to find the answer if you didn't know it was 7, we could ask how many groups of 4? 28 divided by 4 equals 7. Right? You know the answer to this, but think of how, if you had 28 objects, how could you break them apart and show division? One way would be a measurement problem where we would say, okay, how many groups of 4? In the real world, though, that's not the only situation that may happen. How many groups of 4? Well, we just broke out 4, we measured out 4, and then 4 more until we ran out and we found that there were 7 groups of 4. This example is called partitive. It's still division, but think of it in a different way. 28 divided by 4. I'm going to ask the question a little differently. How many will be in 4 groups? With measurement, I said how many groups of 4? In this example, I'm going to say, hey, there's 4 groups. How big are the groups? In the real world, we'd solve it kind of like dealing cards, parting out the cards. You get one, you get one, you get one, you get one, and so on until we run out. This is called partitive division. We encounter this in the real world just as we do measurement. All right, I think that's about all I can stand for now related to addition, subtraction, multiplication, and division. My purpose of this slideshow was just to demonstrate to you that there are many ways to model addition and subtraction, multiplication, and division in the real world, and we definitely should be doing it when we're introducing these operations.